There are four concepts that are covered in this unit. The first one is work, then there's power, kinetic energy, and gravitational potential energy. Let's look first at work. First, we need to know that energy is defined as the ability to do work. So energy and work are quite often interchangeable. We also need to know that work is defined as the product of the force applied to an object and the displacement of that object in the direction that the force is applied. In other words, only the component of the force that is applied to an object that is in the same direction as an object can be used in calculating the amount of work that is done. So there are a couple examples where even though a force is applied to an object and an object is moving, there's no actual work being done. One example would be if we have a man standing here and he's got a string, and on the end of the string there's a ball, and that ball is whirling around in a circle. The string is applying a force to the ball in that direction, but the ball is moving in that direction. The force and the direction are 90 degrees to each other. In other words, there is zero component of the force of the string on the ball that is in the same direction as the motion of the ball. Therefore, there is no actual work done on the ball by the string. Another example would be if you had a box sliding on ice. Let's assume that's not a hill, it's a straight line. Okay, the ice or the box is moving on the ice in this direction, and you push down on it with a force of 10 newtons. Let's say the box moves 3 meters. No work is done in the time that it takes for the box to move the 3 meters. Again, that's because the force is straight down and the box is moving straight sideways. Again, assume this is a straight line, it's not actually a hill there. Okay. So that concept can then be extended to this drawing here, where work is equal to the force times displacement times cos theta, or the angle between the displacement and the applied force. We know from our work in Unit 1 that any vector can be broken into a vertical component and a horizontal component. It is only the horizontal component that is used in the calculation of work. How do we know what the horizontal component is? Well, our understanding of trigonometry tells us that if this is the hypotenuse, this is the opposite side, and this is the adjacent side to the angle theta, then cos of theta equals adjacent over hypotenuse, which means adjacent, which we're looking for, adjacent is equal to h cos theta. In this case, the hypotenuse is the force that is applied. So the force in the direction of the box is equal to the total force times cos of the angle, which is why this equation becomes this equation. So that so you can actually see it, so the pen's not over it. But it becomes this equation here, FD cos theta. Now, if theta is 0, in other words, the force is in the same direction, well, let's grab a calculator. Go 0 and cos, and we get 1. Cos of 0 is 1. So in other words, you're not changing it at all, right? Because F cos theta, if theta is 0, is F times 1, which is just F. Therefore, the entire force is in the same direction as the component, and you don't have to worry about putting the cos theta in. Let's look at a specific example. In this example, this box is moved a distance or displacement of 5.2 meters in the horizontal by a force of 200 newtons, 35 degrees to the horizontal. We want to know how much work is done on it. The first thing I'm going to point out, though, is this little line here. Okay, this little line here above the above the 0. What that means, maybe what I'll do is I'll use a highlighter to highlight it instead. Okay, there we go. That that line above the 0, what that means is that it's rounded off to the nearest tens. Okay, it's rounded off to that place, which means that this number has two significant figures. So does the angle, so does the displacement, so our answer is going to have two significant figures. That's important to note because that's the way that it's written on the final exam. And in most scientific writing, actually, a straight line above a digit means that that's what the number's rounded off to. Okay, so we want to find out what the work is. Work equals force times cos theta, get the horizontal component of the force, times the displacement, which equals 200 newtons, round to the nearest 10, times cos 35 degrees times 5.2 meters equals, pull out our calculator again, 35 cos is that, times 200 times 5.2 equals 800. Now rounded off to two significant figures, it's going to be 850. Line above the 5, Newton meters. If we look over here, unit for work is the Newton meter. 1 joule, capital J, is the amount of work done when an applied force of 1 Newton produces a displacement of 1 meter. In other words, 850 Newton meters is 850 joules. Okay, let's look at the next concept. Next concept is power. Power is the rate at which work is done. It can also be regarded as the rate at which energy is used. So power is equal to work over time, a rate of which work is done. But work is also the expenditure of energy, or the use of energy. So power is also equal to the amount of energy used over time. The SI unit for power is watt, when 1 watt is equal to 1 joule per second, or 1 Newton meter per second. Okay, so let's look at an example. A man pushes a sled on frictionless ice with 15 newtons of force and moves it 12 meters in 4.5 seconds. How much did the man use? Sorry, how much power did the man use? Let's just fix that up. How much power did the man use? Okay, well, power is equal to work over time. And work is equal to F cos theta D. In this case, we can assume that the force of 15 newtons is in the same direction of movement because it doesn't give us an angle. Therefore, work is just equal to F, it's supposed to be an F, try that again, FD. Therefore, power is equal to F D over T equals 15 newtons times a displacement of 12 meters divided by 4.5 seconds equals 40 and this is 15, 12, 4.5, two significant figures in each, so it's 40 rounded to two significant figures, and that would be Newton meters per second. A Newton meter per second is a joule per second is a watt, so 40 watts. That's how much power he uses, and of course a line over it. That's our answer. Okay, next concept, kinetic energy. Kinetic energy is the energy of motion. In other words, it's how much energy an object has due to the fact that it's moving. It's equal to 1/2 times the mass of the object times its velocity squared. EK equals 1/2 mv squared. The units for kinetic energy, as for other forms of energy, are joules. The joule is a kilogram times meter squared per second squared, or 1 Newton meter. If we look at this, we can see that, okay, 1/2 of 1/2 mass is kilograms, velocity is meters per second, square that, you get meters squared per second squared, so you get kilograms meters squared per second squared, Newton meters. Yeah, the units work out. In an elastic collision, kinetic energy is conserved. That's a very important fact, and we'll get into that in some later questions. However, it is very important to note that in an elastic collision, all kinetic energy is maintained. Okay, when a bullet, looking at this example, when a bullet that weighs 8 grams leaves a 9 millimeter pistol, its velocity is 365 meters per second. What is its kinetic energy as it leaves the barrel? Well, first of all, we notice that our units are in grams. We need to change that to kilograms. So that's going to be 0.008 kilograms. We use our formula, EK equals 1/2 mv squared equals 1/2 of 0.008 kilograms. Actually, sorry, that should be 0.0080 kilograms because we have two significant figures. We need to keep two significant figures here. Times its velocity of 365 meters per second squared equals our calculator, 365 65 squared times decimal 0.008 times 0.5, 532.9, 532.9 kilograms meters squared per second squared, which is a Newton meter, which is a joule. Now we have two significant figures and three significant figures, so we can only have an answer to two significant figures, which means it's the 3, so equals 530 joules rounded to the 3. Okay. The final concept that we've talked about in this unit is gravitational potential energy. Gravitational potential energy is the energy stored as a result of the position of an object relative to the ground or some other arbitrary reference. Generally, though, we do measure gravitational potential energy relative to the ground. All right. It's important to note this. The total mechanical energy is the sum of the kinetic energy and the gravitational potential energy of an object, and it always remains constant. It's the law of conservation of energy. In other words, if an object is, say we've got a ball here, and we've got the ground. Up here, the ball is not moving. You're hanging onto it with your hand, okay? So there's a dude here hanging onto this ball, this hand. That ball has a certain gravitational potential energy, measured or calculated by multiplying its mass times the gravitational constant, which near the Earth's surface is 9.8 meters per second squared. 1 second. Okay, and that can also be written as 9.8. Sorry, 9.8 newtons per kilogram. All right. Now, when you drop that ball, it's going to lose gravitational potential energy because the height is dropping, right? So that h is getting less as you drop the ball. The ball's moving down here like this, gets about here. Now it has a lot less gravitational potential energy. However, it has kinetic energy because it's speeding up, right? 1/2 mv squared. Its velocity is increasing, therefore its kinetic energy is increasing. The total mechanical energy is equal to EK plus EG, and that is always constant. So in other words, whatever amount of gravitational potential energy it loses here because it's dropped to a lower height, it gains in kinetic energy by speeding up. That's a very, very important concept to understand, that the total mechanical energy always remains the same. Now in real life, there's air friction on this ball dragging it down. So some of the gravitational potential energy is actually converted to heat energy due to friction on the ball. It's a very small amount, but there would be some there. And therefore, EK plus EG might not quite equal the same amount all the way down. But in the type of problems you're going to be working on, you generally ignore air resistance, friction, things like that. And therefore you can say that yes, EK plus EG is always a constant. Let's look at the example. A ball of mass 0.25 kilograms is dropped from a height of 5.0 meters from the ground. What is its gravitational potential energy before it is dropped? Okay, so before we drop the ball, what's its gravitational potential energy? EG equals mgh equals 0.25 kilograms. It's always important to include your units in your calculations. Times G, which is 9.8 newtons per kilogram, times a height of 5.0 meters. And that equals 0.25 times 9.8 times 5 equals 12.25. Now what are our units? Well, kilograms, newtons, and meters are on top, kilograms on the bottom. Kilograms are going to cancel out, and we're left with newton meters on top. Newton meters get rid of that. Newton meters, and a newton meter, of course, is a joule. Now we have two significant figures and two significant figures. 9.8 we can take to be two significant figures. So our answer needs to be two significant figures. So this is going to round to just 12 newton meters or joules. So that's the answer to 1. Number 2, ignoring air resistance, what velocity will it have when it hits the ground? Aha. Well, when the ball hits the ground, the entire gravitational potential energy has been converted to kinetic energy. Therefore, its kinetic energy is going to be 12 joules as well. And if we go back, we know that kinetic energy is equal to 1/2 mv squared. We know the mass, we know the kinetic energy. We can calculate the velocity. So, let's do that. Now, EK equals 1/2 mv squared. Therefore, V equals the square root of 2, oh boy, this thing is frustrating to write with, 2ek over m is equal to square root of 2 times, now kinetic energy, all gravitational potential has been converted to kinetic, so we have 2 times 12 joules divided by mass, 0.25 kilograms. And that equals 2 times 12 divided by 0.25. 2 times 12 divided by 0.25, and then square root that. There it is. get 9.7979, etc., etc., etc. We've got two significant figures still only, so we get to keep two significant figures. We get 9.8. Now, what are our units? Well, it looks like, well, what's a joule? A joule is a Newton meter. A Newton is a kilogram meter per second squared. So, see if I can find some open space here. I'll just create a new page. Let's look at this, because this is important. This is an important way to check your answer. Our answer is the square root of joules per kilogram. Square root of Newton dot meter per kilogram. A Newton is a kilogram meter per second squared times meter divided by kilogram. The kilograms cancel. This becomes square root of meters times meters, so meter squared per second squared, which leaves us with meters per second when we take it out of the square root. Therefore, when we go back to our question, yeah, that makes sense. We're looking for a velocity, meters per second. We must have plugged the numbers in right because our units are working out right. So it's 9.8 meters per second. Now, you are going to run into cases where you have questions that combine concepts, combine these concepts. For example, this one. Let's look at this example. How much force, okay, so it looks like we've got a box of 35 kilograms being pulled by a force of 450 newtons, 30 degrees above the horizontal, and it moves horizontally 8.4 meters. Okay, how much work is done by the vertical component of the force? Trick question. The vertical component of the force, in other words, that part, is at a 90-degree angle to the displacement. Therefore, no work is done. So the answer to 1 is 0 joules. 0 joules of work is done by the vertical component because it's in perpendicular direction to the displacement. Second question, if the box started at rest, what is its final kinetic energy after it moves the 8.4 meters on a frictionless surface? Okay, well, we know that, looking back to here, work is equal to the amount of energy used, or the amount of energy changed. Well, if work is equal to energy, and they're interchangeable, and they want to know what its final kinetic energy is, because it's on a frictionless surface, there's no heat energy created. Therefore, all the energy is turned into kinetic energy. In other words, the amount of work done on the object is equal to its final kinetic energy. So it's really just calculating the work. So in this case, because it's a frictionless surface, energy kinetic is equal to work. And work is equal to F cos theta d. So EK is equal to F cos theta d is equal to 450 newtons, rounded to the nearest 10, times cos 30 degrees times 8.4 meters. 30 degrees times cos, or cos of it, times 450 newtons times 8.4 meters. And we get 3,273.57, etc. Newton meters, right? Newton meters, or joules. Okay, this is rounded to the 5 here, so that's 2 significant figures. The angle has 2 significant figures. The distance has 2 significant figures. The answer has 2 significant figures. So this would be 3,300 joules, rounded to there. Now this could also be written as 3.3. That's 3.3 kilojoules. Either one would be correct. But on the final exam, when you're working with, excuse me, when you're working with multiple choice answers, it may be written either way, and you'll have to be careful of that. Okay, let's look at another combined example. A car is taken to the shop to be fixed and is lifted up on the hoist. If the car weighs 1.1 times 10 to the 3 kilograms, that's 1,100 kilograms, and the hoist has a power rating of 9.3 times 10 to the 2 watts, how long will it take to lift it 2 meters? Okay. Well, what are we wanting to know? We're wanting to know time. We know the motor's power rating. Okay, so let's look back at our concept of power. Power is equal to work over time, or energy over time. Okay, we know power. We want to know time. Okay, do we know energy? Well, no, it doesn't tell us how much energy is used. However, we know the mass, we know the height, therefore we can calculate the gravitational potential energy. Mass, height, and g is a constant, so we can calculate the energy. So, we're going to look at power equals Eg over T. Therefore, T equals Eg over P. And we know that Eg equals mgh. Therefore, T is equal to mgh over P. We know the mass. G is a constant, 9.8. We know H. P, we know P. We can calculate this. Equals mass, 1.1 times 10 to the 3 kilograms times G, 9.8 newtons per kilogram, times a height of 2.0 meters, divided by a power of 9.3 times 10 to the 2 watts, equals, now 1.1 times 10 to the 3, that's 1,100 kilograms, times 9.8 newtons per kilogram, times 2 meters, divided by 9.3 times 10 to the 2. Well, times 10 to the 2 means we move the decimal place over 2. That's 930 watts. And we're left with 23. Now, time should be measured in seconds, obviously. So, I guess first of all, let's look at two significant figures all the way through. So yeah, it is 23 seconds. Okay, so 23. Now it should be seconds because we're measuring time, but let's double check our units and make sure. We've got kilograms times newtons per kilogram times meters. Okay, well, first of all, kilograms are going to cancel. And we're just left with newton meters per watt. Newton dot meter per watt. Well, a watt is a joule per second. A newton meter is a joule. And a watt is a joule per second. Therefore, the joules cancel out, the seconds move to the top, and we're left with seconds. The reason the seconds move to the top is that, okay, if we have joule divided by joule per second, any time in math, you divide by a fraction, okay, and joules per second, that's like a fraction, right? One over the other, so you're taking joules, dividing by a fraction. It's the same as multiplying by the inverse. So this is the same thing as joules times seconds per joule. Joules cancel, seconds left on top, and we know that this is seconds. So we have 23 seconds. That's how long it will take to lift that car up 2 meters in the air with that hoist. Okay, let's look at another example. A plane is flying at 100 meters per second and drops a supply crate to an isolated town surrounded by flooding. The plane is 750 meters above the ground. What is the total mechanical energy of the crate the instant is pushed out of the plane? Okay, well, mechanical energy is equal to, so we could call that, let's just call that EM, and it's equal to EG plus EK. Okay, gravitational potential energy of the crate. Well, the crate is 750 meters above the ground. Oh, this question is missing something. Sorry. You wouldn't actually be able to answer this question. The supply crate of mass, let's say 50 kilograms. And we'll do, let's do 53 kilograms. That way we know for sure how many significant figures there are. Okay. My apologies. That question didn't have enough information. So a plane flying 100 meters per second drops a supply crate of mass 53 kilograms to an isolated town surrounded by the flooding. The plane is 750 meters above the ground. What is the total mechanical energy of the crate the instant it is pushed out of the plane? Okay, now we can calculate EG. EG equals 750 meter, or EG equals, equals mgh plus 1/2 mv squared. Okay, its mass, 53 kilograms times 9.8 newtons per kilogram times a height of 750 meters plus its kinetic energy, which is 1/2 mv squared, so 1/2 of 53 kilograms times velocity, it's traveling 100 meters per second, 100 meters per second. Square that. By the way, we'll just say that this is, draw a little line above that 0, say it's 2 significant figures. Okay, so we can calculate this out, and we're going to be equal to, the calculator, 53 times 9.8 times 750 equals 38,900. Sorry, 389,550 what? Okay, well, kilograms cancel out. We're left with Newton meters, which is a joule. Plus 1/2 of, okay, so let's bring out our calculator again. So 0.5, 1/2, times 53 kilograms times 100 squared equals 265,000. 265,000. Now this is going to be kilograms meters squared per second squared, right? Because the meters square are going to square, the seconds are going to square, so we're going to be up to kilograms meters squared per second squared. A kilogram meter per second is a Newton, so we can take that out, and we're left with just a meter, so it'd be a Newton meter. One Newton meter is a joule. So good, our units are working out. We add these together. Oops. 89,550. After that, now we can only go to two significant figures, though. So that's going to be equal to 650,000. 650,000 joules, or 650 there we go, it's written better, kilojoules. Either one is correct. Okay, so that's its total mechanical energy. Now, ignoring air resistance, what is the total mechanical energy of the crate when it is 500 meters above the ground just before the parachute opens? Okay, so if we're ignoring air resistance, that means that all the gravitational potential energy that the crate loses by dropping that 250 meters is completely converted to kinetic energy, which means that the total mechanical energy isn't going to change, right? Mechanical energy always stays the same, and provided there's no friction involved, that means it's always the gravitational potential plus the kinetic energy. Provided there's no friction, i.e. ignoring air resistance, it doesn't matter what height this is, what height they tell you here, you don't need to calculate it because you know it's the same at the top of the, right when it's pushed out of the plane, all the way down to the point that it hits the ground, or in this case, the parachute opens, in which case you would not be able to ignore air resistance anymore. If it has a parachute hanging from it, obviously there would be a lot of friction then that you wouldn't be able to ignore. But in this case, we're saying just before the parachute opens on the crate, and we're going to ignore the air resistance on the crate itself. Well, then we know that the mechanical energy doesn't change, and so the answer again is going to be 650 kilojoules. It's going to be 650 kilojoules at 700 meters, at 650 meters, at 600 meters. All the way through that fault, the mechanical energy doesn't change. It's just that some of the gravitational potential is converted to kinetic. Okay, well, that's a good review. Oh, there's one more type of question that I didn't think of until I was going through the review, and that is here in elastic collision. Let's take a billiard ball example again. Let's do one of those. So let's say the example that we're going to give is a cue ball of mass, I don't know, let's make up a mass, I think if I can remember it right, I think it was 0.16 kilograms. Cue ball of mass 0.16 kilograms, traveling at, let's say, 3.5 meters per second, hits a numbered ball of mass 0.17 kilograms, and bounces off at a speed of 2.6 meters per second. Assuming an elastic collision, what is the speed of the numbered ball after the collision? Okay, well, again, in an elastic collision, kinetic energy is conserved. In other words, the total kinetic energy of both balls beforehand is equal to the total kinetic energy of both balls afterwards. So, put that out. Let's say, well, E K kinetic energy of the cue ball initially plus the kinetic energy of the numbered ball initially is equal to the kinetic energy of the cue ball final plus the kinetic energy of the numbered ball final. Okay, kinetic energy of the cue ball initially is 1/2 mv squared plus 1/2 m. Now this should be numbered initially v squared, and this should be numbered initially v squared equals, yeah, well, you get the idea that those are all the number, or the, sorry, this would be cue ball initially, that they're follow the same conventions, that this is like cue ball initially, the number ball initially, the cue ball finally, the number ball finally. So I won't bother writing those subtexts in there. So 1/2 mv squared plus 1/2 mv squared. Okay, mass of the cue ball, 0.16 kilograms times its velocity, 3.5 meters per second squared, plus 1/2 0.17 kilograms times 0 meters per second squared equals 1/2 0.16 kilograms times 2.6 meters per second squared plus 1/2 0.17 kilograms times v squared. The only one we don't know is v. So let's work some of this out a little bit. So, and then we'll solve for b. Okay. 0.5 times 0.16 kilograms times 3.5 meters per second squared equals, that's 0.98, and that's kilograms meter squared per second squared, which is a Newton meter, which is a joule. Joules plus, now this one is obviously going to be 0 joules because you're multiplying by a speed of 0, is equal to 0.5 times 0.16 kilograms. That's this stuff here. 0.5 times 0.16 kilograms times its final speed of 2.6 meters per second squared equals 0 decimal 5408 joules plus let's go 0.5 times 0.17, so 0 decimal 0.085 kilograms times v squared. Okay, so, well, how can we solve for this? We can solve for this by taking that, adding it to that, you get 0.98, subtract this, so we've got 0.98 joules minus 0.5408 joules equals 0.4392. 0.4392 joules is equal to 0.085 kilograms times v squared. Used to be a way to extend my page here. Don't see it anymore, so I'll just create a new page here. I'll just go up here. Copy that onto the new page so you can see where I was going from. Okay, so we've got this now. So we can divide out to get v squared alone. So 0 decimal 4392 joules divided by 0 decimal 0.085 kilograms is equal to v squared. Okay, our calculator, 0.4392 joules divided by 0.085 kilograms equals 5.167. We'll just keep four significant figures right for now. So we know we have enough and we'll round off at the very end. Equals v squared. Now, what are the units here though? Joules per kilogram. Okay, well, let's see. A joule is equal to the joule per kilogram, which is equal to a Newton dot meter per kilogram, which is equal to well, Newton is a meter. Go over here. A Newton is a meter. Sorry. A Newton is a kilogram meter per second squared times by meter again, divided by kilograms. Kilograms are going to cancel. We're going to be left with meter squared per second squared. So this is meter squared per second squared Square root that number. And we get 2.27. Now, how many significant figures can we have? If we go to the very beginning, we've got 2 here, 2 here, 2 here, 2 here. It looks like we can have 2 significant figures in the end. So V is equal to 2.3. Now, meters squared per second squared, when you square root that, of course, you just end up with meters per second. And that makes sense because we're looking for a velocity. So, yeah, 2.3 meters per second is the final velocity of the numbered ball. And we have our answer. All right, that's a 55-minute review for the exam. Hopefully covers everything you should need to know for the test and for the final.